So the last section in this chapter has to deal with inverse functions. And what an inverse function is something that allows you to take a function and just kind of see what happens if you deal with, for lack of a better term, the opposite of it. So if you imagine for class, we've dealt with a lot of specific things where we ask you to find what this is. And it could be any number. And in terms of a picture, we have a domain, and we would map it to some value in the range. Let's say it's 10. So we have this function, doesn't matter what it is, that gives us a value of 10. This is based by some rule that whatever it's defined as is a function. What's also interesting to try and find is a way to get back to any point that we pick. And we define that as an inverse function. It does the exact opposite. It takes whatever you have and maps it back to your original values. So you see this little -1 that looks like an exponent. That means inverse. So what we're going to be talking about is how you find inverse functions. And for this first example, they're asking you to do it based on a pattern that you see. It says to find it informally. So we have this function, then it says to verify something. Now, with this, I want to talk about a property first. Something that's very unique about functions and their inverse. Okay? And what that is if I take any function and compose it with its inverse, or do the exact reverse, take the inverse and compose it with the original function, the only thing I'm going to be left with is x. And you'll see what that means in just a minute. But what I want to talk about is how this function works and how we can find an inverse. So I can pick any values that I want. Let's just do 1, 10, and 25. And in this function here, the function values are going to be 4, 40, and 100. So now what we have to think about is if we have functions that are numbers that are mapping to these three, we have to think about this in reverse. So what numbers I'm going to have and what the inverse function is going to do, well, it has to take every number that we got for an answer and map it back to its original. And if you look at this, you say, well, we're timesing it by 4, so how do I get back to its original? Well, hopefully you can see that the obvious answer is to take it and divide it by 4 or times it by a fourth. So this is your inverse function. This is the inverse function. Now, we have to check this, and the check for this one's going to be fairly straightforward. So what I'm going to do is I'm going to take my original function and compose it with the inverse function and see what happens. Well, the outside function was 4x, and I'm going to replace the x with the inverse function, which is x over 4. And if you cancel the 4's out, you're left with x. If I do the exact same thing with the inverse and compose that with the original function, the outside function is x over 4, and I'm going to replace x with 4x. And again, the 4's cancel out, you're left with x. So what does this mean in terms of a number? Well, if I take any number, let's just say the 100, for an example. The inverse function said to divide by 4. So if I divide this by 4, I get 25. So this whole thing here is 25. So I'm going to replace that with 25. The original function says to multiply it by 4. So if I multiply it by 4, I get 100, which is the number that I started with. I can do that with any number for this. Any number I pick, if If I plug it into the original function and then the inverse, I'm going to be back where I started. So to verify if something's an inverse or not, you see we have this and says which of the two functions here is an inverse. So what we need to do is we need to take this first of all and plug it in for x to see what happens. So what this looks like in notation is this. And we're going to see what happens and see if we have anything that cancels out. So instead of x minus 2, it's going to be 5 over x minus 2 minus 2 over 5. So I replaced x here with f of x. Well, this doesn't have that denominator, so I need to give that a common denominator. So I'm going to times it by x minus 2. So it becomes 5 minus 2 times x minus 2 all over x minus 2 all over 5. Now, doing some quick algebra here, I'm going to distribute this. I get a negative 2x plus 4. So I get 5 minus 2x plus 4 all over x minus 2 all over 5. Now this is going nowhere fast, but we're going to simplify it to show that it's not equal to this. So we have 9 minus 2x over x minus 2 divided by 5. That's the same thing as timesing it by 1/5. I get 9 minus 2x over 5 times x minus 2. Can't do anything else with this. And you can see after all that mess, we didn't get the inverse like we should have. We should have gotten just an x value back, just x, called the identity. Okay? So we didn't get that. So all of this was to show that this one wasn't the right one. Well, if there's only one left, that means that it's probably this one, but we have to check it. All right? So I'm going to take and plug in for x in this function. So 5 over x minus 2 plus 2. I'm going to divide this. It's the same thing as taking and timesing by the reciprocal. These x's can cancel out. So I'm left with x minus 2 plus 2, which equals x. So I'm left with x here. Now I have to check the other way. I have to check and go the exact opposite and see what happens when I plug this one here into that x. So I have 5 over x plus 2 minus 2. Well, these 2's cancel out right away. So I'm left with 5 over x, which is equivalent to 5 times x over 5. Again, the x's or the 5's cancel out. You're left with x. So it turns out both cases you are left with just the identity function. So these are the inverses of each other. So h of x is the inverse. Now you might ask, is it okay or is it enough to say, is one of them good enough to check? And the answer is going to be no, because sometimes it might not work for both of them. So what I want to look at real quick here is how a graph looks for the inverses of some function and how it relates to what it means in a graphical standpoint of how inverses look. So what I want to do is graph this function very quickly. So you see it's just a regular line with a slope and a y-intercept. So I'm going to go down to 3 and up 2 over 1. And what I have is one line, and if I draw a line through them, there is my line. So I'm going to do the exact same thing with the next one. But if you look at the next one, Notice that it's not in the right format. It's not in the right format for us, so we have to put it in the right format. So I'm just going to distribute, and I get 1/2 x plus 3/2 for my inverse. So I'm going to start at 3/2, which is about right here, go up 1 over 2, and I'm going to make a line for both of those too. So here is my second line. Now, we have the reason for graphing this is specifically to show that there's a relationship between the two, and the reason is that if you look at this graph in terms of the line y equals x, you will notice something, and if I can get the right type of line to show up, I will show you what it looks like. The line y equals x looks just like this. And what you notice is that this is a mirror image across this line for each one of these. It doesn't matter where I pick, it's a mirror image directly across from it. So these two are reflections across the line y equals x. Okay. Now, if you don't graph it very well, there's no way to prove that, but if you see it, you can see how it just kind of splits it right down the middle on both sides here. The last thing I need to talk about very quickly is the ability to tell if something is one-to-one. Now, we've talked about specifically what makes something a function. And what makes a function is the fact that if something is a function, x values are only paired with one y value. Okay? So we use the vertical line test to test that. If something is one-to-one, that's a new type of function, and that there's a purpose for talking about that type of function. And the reason is because it's going to allow us to talk about inverses. But a one-to-one function means that each y value in a function comes from only 1x. So we're talking about y values, and in the next video I'm going to talk about how you see this, but each y value is only coming from 1x, and I'm going to show you one that is an example and one that's not, and how it relates to one-to-one functions.